right, I'm going to walk through the solution to this practice problem. Hopefully you've had a chance to try it. If not, just pause the video. In this one, we're asked not to calculate the activation energy. Instead, we are given the activation energy. It's 40 kilojoules per mole. And we're asked to find out what is the change in the rate if we increase the temperature from 70 degrees to 80 degrees. So when we say change in rate, what that says to me is that what I really want here is I want to know what is that ratio of K2 to K1. That's what we need to find, because that's going to say if my rate doubled or if my rate quadrupled. We're just trying to figure out what that ratio is. We don't need to know the exact value of either of those, just the amount of change that occurs between them. Okay, so let's kind of unpack some of the information given here and get it into units that I know we're going to need. So when we're going to be using our equation, the natural log of our ratio of rate constants is equal to the negative of our activation energy over R times the change in the inverse of our temperatures. I put too many twos. So using this, we know our R value is going to be equal to 8.314 joules per mole, Kelvin. So we need our temperature in Kelvin, and we need our activation energy in joules per mole. Right now it's in 40 kilojoules per mole. So our activation energy needs to be converted. All right, so we have 40,000 joules per mole. For our temperature, T2, we're at 80 degrees Celsius. And we need that to be in Kelvin. You could do 273 or 273.15, whatever you want to do. So that's going to be 353 Kelvin. And for T1, my 70 degrees Celsius is going to be equal to 343 Kelvin. All right, so now I have the information that I need. And again, my goal here is to calculate this ratio of Ks right there. So I'm going to plug in these values and see what this looks like. We're going to have the natural log of our ratio of rate constants. It's equal to negative 40,000 joules per mole divided by my 8.314 joules per mole Kelvin, all over, or times 1 over 353 Kelvin minus 1 over 343 Kelvin. Whew, it's a lot. So I'm going to just plug this into my calculator, everything on the right-hand side, and I'm going to get the natural log of my ratio of rate rate constants is going to be equal to 0.397. All right, so from there, I just now need to do e to the power for both sides. So it's like this. So that way I can isolate my ratio of Ks. And I'm going to get a value that is 1.487. So it's really going to be 1.5. And that means that my rate increases by 1.5 times, will be 1.5 times faster after I increase it 10 degrees. So I can write that out. So the rate at 80 degrees Celsius is 1.5 times faster.